In this video, we're going to review a little bit about sample proportions as well as talk about sample means. So in a previous election, pollsters believed that 85% of a population was in favor of voluntary withholding of life support systems for the terminally ill. To judge whether this issue should be important in a current election, pollsters survey 1,528 people and find that 1,238 support voluntary withholding. What was the probability of finding this proportion or less if the data that suggested 85% was true? So, the first thing we need to do is check our conditions. If you remember, obviously there's kind of that zero condition that we needed a simple random sample. We should always be checking for that. Okay, it doesn't say that explicitly, but it is pollsters, so we're hoping they took a good sample. Okay, so condition one. Condition one, remember, ensures that we have some variability. If we asked everybody, then of course we would know the percentage. There would be no reason to find the standard deviation. So this is the sample size, 1,528, must be less than or equal to 1/10 of the population size. We call it sometimes the 10% rule. This seems like kind of a nationwide kind of poll, right, for an election. So I'm going to say yes, we have achieved that. We're less than 1/10 of the population. Condition two, this is used to ensure normality. We take our sample size and multiply it by the proportion we were given, as well as its complement. And the reason for doing this is really to ensure that two things. Our sample size was large enough, but also to ensure that we aren't skewed. Being, if the proportion was 0.99, then it would be very hard to not be skewed to the left. Okay, so these two values are 1,298.8. I'm going to say 0.9 and 229. Both of these values are larger than 10. That's what needed to be true for both of them. So we have fulfilled both conditions. So what we can do now is we can say, well, we have a normal distribution, should be normal around 0.85. And our standard deviation, remember, is 0.85. There's 1 minus 0.85 over that sample size. Okay? And if you calculate, what is this p hat? Okay? My p hat is 1238 divided by 1528. This comes out to be 0.81. So that's what we're doing. We're trying to find the probability of that 0.81 or less using our normal CDF. Okay, so I typed that in. You can see that answer. It is an extremely small probability. 6, I guess, times 6 to the negative 6, or maybe you wanted a couple more decimals. You could say 5.97 times 10 to the negative 6. So it's small. So what that means, the small probability, is really one of two things. Either we had a sample that just didn't match up to the population for whatever reason. There's sampling error, there's bias. It's not impossible that this sample occurred, it's just unlikely. The other thing that might be true is that 85%, maybe that data was collected the last election cycle. Maybe it's old. That 85% might be from 2 years ago or 4 years ago, and maybe the feelings really have changed. Maybe it's less now than it used to be. So that's how we kind of use this probability, is to make judgments about our sample or the existing data. And the thing we always have to remember is existing data like this number, 85%, that came from a sample as well. There's no census taken. Okay, so we're going to use this more and more and talk about kind of formulating our arguments in the coming days and weeks. So the big idea we talked about last week, if you'll recall, is that when we start talking about samples, like sample proportions or sample means, those things have less variability than single observations do. And I wanted to just show you a couple examples. You can see this is taken from a population that was normally distributed, and if I hit play, you can see that random things are drawn, and then on the bottom, the mean is calculated. Okay? So when you start upping your number of samples, this ends up very, very normal with a smaller variability. Okay? And that makes sense. The sample means will get smaller. So again, you see this, the individual data is dropped down, and then the blue is the mean of that data. Okay, so you can see as I take more and more samples, I was upping it 5 samples at a time, it gets much more normal, and then I did a 10,000. Okay, so now I want to talk about what happens if it's non-normal. Okay, so take a look at this, and you can see I took very small samples and calculated the average, just samples of 2. And then I started adding 5 more sample means down there, and then I did 10,000. And you can see it begins to look mound-shaped, but it takes an awful lot to make it look mound-shaped. Whereas this one, still that same distribution, but I up my sample size quite a bit. It's a little fuzzy to see. I was taking a sample of 25. So 25 observations get dropped down, and then you'll see once it's done, the mean is calculated. And if I do 5 of those, and I kept adding more and more, and then I made the jump to 10,000, and you can see that even though the original distribution was just uniform, you take all these little observations, calculate the mean, the means are going to be normal, regardless of what the original distribution looked like. Let's begin talking about sample means. The heights of redwood trees that are over 150 years old are approximately normally distributed with a mean of 185.2 and a standard deviation of 7.1. If we went to Yosemite National Park and took a simple random sample of 25 such trees, what should the mean of our sample be? Well, of course, the mean should be 185.2, but we understand that it might not be. As the sample size increases, what should happen to the estimate of our mean? Well, the limit as n approaches big N of our sample means, of course, should be the population mean. Now, sample means have less variability than individual observations. We've said that before. We looked at a couple of videos. So here's the question. How do we adjust our original variability to reflect that as the sample size goes up, the amount of variability goes down? So I know, we've talked about that typically we don't adjust standard deviations, we do variance, and it actually is as easy as dividing by n, okay, that the standard deviation of our sample means. But then we want to go back, so it's the square root. So this simplifies, of course, to just be standard deviation over the square root of n. Okay, so this is how the sample means variability works. Because remember, individual observations have a standard deviation, but the sample means will have a smaller deviation. In the next video, we're going to talk about the conditions for this as well as do an example.